Welcome back to the channel. Today we are diving deep into 3 essential administration and monitoring tools on openSUSE Linux. We will cover time synchronization with Chrony, configuring system logging, and support config for system diagnostics. Whether you are a sysadmin, network admins, database users, and anyone who cares about having the correct system time, or just someone trying to keep your system running smoothly, these tools will help you stay on top of your system's health and performance. Let's get started. Time synchronization. Time synchronization is crucial in any Linux system, especially in environments where multiple machines interact. If time drifts out of sync, it can lead to issues in distributed systems, troubleshooting logs, and even security problems. The NTP or Network Time Protocol is a system designed to synchronize the time between computers over a network. Maintaining accurate system time is important in various situations, from databases to clusters. In openSUSE lib, we use Chrony as the NTP Network Time Protocol service. Chrony is fast, accurate, and particularly useful on systems with intermittent or unstable connections. Since openSUSE lib 15, Chrony has been the default NTP implementation. Chrony is composed of two parts, ChronyD, a daemon, and ChronyC, a command line tool for monitoring and modifying ChronyD. Let's confirm that Chrony already installed on our system. We can do sudo zipper info and Chrony, and we press enter. Now let's verify that the service is running. Sudo system control status and ChronyD. Okay. Now let's check the NTP configuration from Yast, and let's go and write Yast here, and we enter our root password. And from the network services, we can find NTP configuration. And let's go through the options there. Here you have the start NTP daemon. And this you can choose when to start the NTP daemon. We have only manually. This will require you to start the Chrony daemon manually. The second one, synchronize without daemon. The system time will be periodically updated without a constantly running Chrony daemon. The third one, now and on boot. This option starts ChronyD automatically on boot, which is recommended setting. You can also configure the source type as either dynamic or static. If you are using DHCP, choose dynamic. Otherwise, static is good for predefined servers. Finally, you can add, edit, or delete time servers from the list. Make sure to use reliable sources. For an example, pool.ntp.org. Like for an example, we can go here and we can choose public. And from here, we can get accordingly here all. You can go through all the sources for NTP. Okay. And again, make sure that you are using a reliable sources like, as we said, pool.ntp.org or maybe SUSE.ntp.org. Now let's manually configure NTP. Chrony is configured using the /etc/chrony.conf file. This file controls how your system syncs time. Let's edit it to include a few NTP servers for more reliable time syncing. Sudo pi etc chrony.conf. Look for the line that begins with pool and replace or add reliable NTP servers of your choice. Here, I'll take this copy and we can add this and another one, but this time I will use openSUSE.spool. Okay, and we can add it like that, or we can add it like this, and another pool. Okay. And also you can specify multiple servers like this. You can say server 1 dot open SUSE dot pool dot ntp dot org. So don't forget, after editing in chrony.conf file, you have to restart the service of Chrony. So let's restart it. Restart Chrony D service. Okay. And there is a note warning in the official documents of openSUSE. Be careful not to enable both Chrony D service and Yast-time sync service at the same time, as they can conflict with each other. So be careful about that. Now let's talk about commonly used options and directives, like the iBurst we saw before in the configuration file. iBurst: when a time source is unreachable, iBurst sends a burst of requests to the server at a faster rate, typically 4 to 8 requests within the first few seconds, to speed up the initial synchronization. Once the server responds, the polling rate returns to normal. This is useful to quickly sync the time after the machine is turned on. Another one is pull interval. The pull option controls how frequently the time server is pulled for synchronization. The value represents the algorithm base 2 of the interval in seconds. For example, pull 3 would result in pulling every 2 power 3 equal 8 seconds. We have another one, max pull and min pull. These options define the minimum and maximum pulling intervals. For example, if you set minimum pull 6 and maximum pull 10, the pulling interval will vary between 2 power 6 equal 64 seconds and 2 power 10, which is equal 1024 seconds. Lastly, we have local stratum. Specifies the stratum level for the local reference clock. The stratum level indicates the distance from the authoritative time source. Stratum 0 represents the most accurate clock, for an example like GPS or atomic clock, while higher numbers indicate less reliable time sources. Setting local stratum 10 tells Chrony that the local clock is a last resort fallback source. Example like local space stratum space 10. Now that Chrony is running, let's verify that it is synchronizing correctly. Run sudo Chrony C tracking and hit enter. The Chrony tracking command provides detailed information about the current status of the Chrony time synchronization on your system. Chrony is a versatile implementation of the Network Time Protocol (NTP) and is responsible for keeping your system's time accurate. The output of this command helps you understand how well Chrony is performing and how synchronized your system is with the configured time sources. Let's break down the output. Reference ID. This is the identifier of the NTP server or other time source that the system is currently synchronized to. It shows either an IP address or a host name, helping you identify the specific time source Chrony is using. If the time source is reliable, you can expect better synchronization accuracy. And stratum. The stratum is the distance from the primary reference clock. Stratum 1 is a time source directly connected to an atomic clock or GPS. Stratum 2 servers get their time from a Stratum 1 server, and so on. Lower stratum values closer to 1 generally mean more accurate time. In this case, 4 means the system is getting time from a stratum 3. Reference time, UTC, Universal Time Clock. This shows the last time Chrony received and processed a time update from the reference server in UTC, or in another word, Coordinated Universal Time. This helps track when the system last synchronized with the time server. If this value is old, it might indicate connection issues or that updates are too infrequent. Then we have system time. This shows how much the system clock differs from the NTP synchronized time. So here in this case, we have this number seconds slow of NTP time. The closer this value is to 0, the more accurate your system's time is. A small difference is normal and expected as clocks are never perfectly synchronized. Last offset. This represents the offset between the system clock and the reference clock from the last update. A positive value means the system was ahead, and a negative value means it was behind. This value helps you see the recent drift in the system clock relative to the reference. Chrony adjusts the system time based on this value. The RMS offset. This is the root mean square, or RMS, of recent offsets, which gives a measure of how stable the system clock is. The lower this value, the more stable your system time is. Higher values indicate more fluctuation in the time synchronization accuracy. Frequency. This is the correction that Chrony is applying to the system clock to compensate for its inherent drift. The frequency adjustment is measured in parts per million. In this case, the system clock is running here, the frequency, yeah, it's a little bit slow by this number 11.609. This shows how much Chrony needs to adjust your system's clock. A high value could indicate that the system clock is less accurate or that there is a hardware issue. Then we have the residual frequency. This is the remaining frequency error after Chrony has made the frequency adjustment. It shows how well Chrony's frequency correction matches the system clock's drift. A residual frequency close to 0 indicates that Chrony's corrections are working well. Large residual mean there is still some error left to correct. Skew. This is an estimate of the error in the system's frequency correction, showing how much the frequency is fluctuating. It is measured in ppm. Lower skew values indicate more stable frequency corrections. Higher values suggest that the clock's drift rate is varying more. Root delay. This shows the round trip time it takes for a request to reach the NTP server and return. It is essentially the network delay between your system and the time source. A low root delay means that your system is close to the NTP server, network-wise, which can improve the accuracy of time synchronization. Root dispersion. This measures the maximum error that could exist between your system's time and the true NTP time due to network delay or clock drift. A lower dispersion value indicates higher confidence in the accuracy of your time synchronization. Update interval. This is the interval between successive time updates from the reference source. Chrony dynamically adjusts this interval based on the system's stability. If your system is highly stable, the interval can be larger, hundreds of seconds. If it is less stable, the interval might shrink. Leap status. This field indicates the leap status of the system clock. Leap seconds are occasionally added or subtracted to keep UTC synchronized. The possible values are normal, no leap second scheduled. Insert, a leap second will be added at the next midnight. Delete, a leap second will be removed at the next midnight. Not synchronized, the system is not synchronized with any time source. Normally, will be set to normal, indicating that there are no leap seconds pending. You can use Chrony, the command line tool, to monitor and configure the Chrony daemon at runtime. You can run Chrony interactively by typing Chrony and entering commands at the prompt, like for an example, sudo Chrony and press enter, and we can write activity. This will give you the status of NTP sources. You can also run the same non-interactive commands. So let's exit from that queue and we write again activity. Just remember, changes made with Chrony are not permanent. If you need to make permanent changes, edit the file /etc/chrony.conf. Okay. Sometimes the system boots without a network connection. Chrony will keep trying to connect to the time server in increasing intervals until successful. You can set time servers to offline mode until the network is up using this configuration in the file sudo vi etc chrony.conf. And let's say for an example, this one, server openSUSE.pool.ntp, you at the end here of line, okay, and save the file, and don't forget to restart Chrony service, Chrony service. And after the system is already booted, you can run this command Chrony online, and the IP or the host name of the for the server NTP server, openSUSE.spool.ntp.org. Okay, that's for it's like dynamic time synchronization at runtime. You can configure it like that if you know that you have some kind of network issue while your system is booting. Now, to view the status of all your NTP sources, you can use sudo Chrony sources -v. This gives you detailed information about each source, including how frequently it's queried and the current offset. That's Chrony. It ensures your system is always synced with the with accurate time, which is vital for server management, especially in enterprise or distributed environments. Okay. System logs are essential for monitoring, troubleshooting, and auditing your system. In openSUSE, the system logging is handled primarily by systemd through journal. The journal itself is a system service managed by systemd. Its full name is systemd-journald.service. Unlike traditional systems where a separate syslog-based service like rsyslog or syslog-ng is used, systemd comes with its own integrated logging mechanism. This makes it unnecessary to run additional syslog services, as all logging events are automatically managed by the journal. Systemd-journal D is a core component of systemd that collects and stores logging information from a variety of sources, including kernel messages such as startup logs, driver issues, user processes, any application running on your system that outputs logs, standard input-output streams, errors from system services like failed service, startups, crashes. The logs are stored in structured indexed journals, making it easy to filter and search for specific information. The service responsible for this functionality is systemd-journald.service, which runs by default on all modern openSUSE systems. By default, systemd-journald stores logs in /run/log/journal, which is a volatile directory. This means logs are stored in memory and are lost upon reboot. However, you can configure persistent logging, which ensures logs are stored permanently, surviving reboots. So let's start doing that by creating mk-var with -b var log and journal, and after that you should make sure about the appropriate permission for the folder. Sudo systemd temp files, create prefix and the path journal, and after that don't forget to restart the service. System control restart system d journal d, and after that you call for flush by using journal control flush. Let's sudo. Here any log data stored in /run/log/journal will be flushed into the created path /var/log/journal. Let's confirm that log journal, and now we have the logs from systemd-journald is persistent and will survive reboot. The journal control command is used to query and view the logs managed by systemd-journald. It provides powerful filtering options to help you navigate through large volumes of log data. So let's start with the basic log viewing. To view the system logs, simply use sudo journal control. This command displays all logs starting from the earliest log available in a continuous stream. Okay. You can also filtering by time. You can filter logs based on time ranges using the --since and --until flags. For example, to view logs from the last hour, sudo journal control since, and we can write here 1 hour ago. Okay. You can also choose to since today, means since the machine started actually. You can also filter based on boot number. Journal control can filter messages based on a specific system boot to list all available boots run. But just remember that we just activated the persistence. Okay, so these filters working uh, accordingly to the persistent, because if you didn't do that, the logs is continue to be saved in RAM and it will not survive reboot or power off and power on for your machine. So don't expect to get logs from yesterday or 1 week ago. Okay, so let's try this. We can do journal control and here list boot, and as you can see we have only one saved since we start the persistent. So every time I reboot my server or machine and I start it, it will add it here. Okay, so we can, if you need to see journal messages from previous reboot, let's give the example. You can say B, and here I can put the ID. So if you have more than this, you just use the ID here. So it is started with 0, next one will be 1, the next will be 2, and so on. And then you can use. If I did that, there is nothing. Okay. Also, you can filter based on fields. You can filter the output of the journal by specific fields. The syntax of a field to be matched is field underscore name equal matched value, such as underscore systemd underscore unit equal httpd.service. You can specify multiple matches in a single query to filter the output messages even more. Also, you may check the manual 7 for systemd.journal-fields for a list of default fields. So let's take an example to show a message produced by a specific process ID. So let's take an example here. And let's, or better, I use top to be more clear. And we can, let's say I would like to check this systemd. Now I will check the X, okay, for the graphical user. So I will take this and I say sudo journal control PID equal and the ID. So no entries for that. Of course, again, because we just made the logs persistent now, so if there are any errors happen before, it will not show. So let's try a random number, or maybe 23, nothing. Okay, let's try the one for systemd. So nothing yet. Let's try this. Okay, so once the logs accumulated, something will be showed here. Also, you can filter by specific service. So for an example, one of the most useful features, as I said, that for systemd, that the ability to display logs specific to a particular service. So for an example here, we can do this sshd and no SSH happen or logs for this service here. For continuous viewing for most recent logs in real time, like if you want to follow new log entries as they are generated, similar to the tail-f command, you can come here and do like that. So any changes happen on the system, it will start to show here as we saw now. Okay. If the journal log data is saved to a persistent location as we did before, it uses up to 10% of the file system the /var/log/journal resides on. To prevent journal logs from consuming too much disk space, systemd-journald allows you to limit the size of log files. You can configure this by editing the /etc/systemd/journal-d.conf file. Also, for a complete file description, you can check the manual 5 journald.conf like that, man 5 journald.conf, and you can check it's rich with all the information you need to configure this file. To clarify this thing here, that etc system D, and if we check this folder, we will not see that file. Why? Because the file actually is in usr lib system D, and we can find the file here. Okay, so if we open this file, here you can read, and what I care about to show it here, that this file here, entries in the file show the compile time defaults, local configuration should be created, and so on. And here, or a copy of it placed in /etc if the original file is shipped in /usr, like in our case, or by creating drop ends in the /etc systemd journald.conf/d directory. The latter is generally recommended. So I will follow the recommendation and I will take a copy of that file because I'm going to change it, and I will drop it there in that path. Okay. So to make my life more easier, I will do sudo and I will do for copy usr lab systemd journal d.conf to etc system journal d, and I will copy the file there. Then from there we can edit the file. For the parameters, vi etc journal system the journal. Okay, the first parameter is system max use. Let's find where the system max use we can search like that, system max. Yeah, we find it here, this one. Okay, this one, maximum space the journal can use on disk. Okay, the second one is system max file size, this one. Okay, this one and this one. The third one is max retention on max retention. Second, the maximum amount of time logs will be stored. So let's try, yeah, this one. Okay, so for example, to limit the journal size to, like, okay, system max use, I will take copy of it and I will edit it here, and let's say 500 MB. Okay, so you can save the file, and system, don't forget to restart the service, systemd and journal d. Yeah, journal d. Okay, now the service is restarted, and the size to save the journal, the logs, is 500 MB. Also, if you didn't notice in the file that we edited before, here we have this command to show you, to display the full config. And if you have the file in that place that we copied, and let's show you. Now we have two files configuration in /usr/lib/systemd/journal, and we copied the file to this path under /etc. So when I run this command, it will show you accordingly, starting from the one that comes with the systemd, the default where the file is reside. So you can see here they are the configuration in under /usr. If you scroll down or go down using the arrow, you will continue to see the config file to the end of it, and you will see here again the file that we copied, and you can check which is commented and which is active. And here, this is the one we put and is active. This is how to check your configuration before you change anything. Systemd journal D manages its own form of log rotation automatically. It compresses and removes older logs to maintain disk usage within the configured limits. However, if you need to manually clear old logs, you can use the following command: sudo journal control vacuum size equal 200 m. This will reduce the total log size to 200 m. But of course, because the size not reached more than 200 m already, because uh, the total, like for an example, let's check this one size sudo to let you know we mean here. So the size is only 17 m, the original. So this will reduce the existing size to this number you put here, the total size of the log. So let's say the log's 1G, 2 or 3 gigabyte. It will reduce it to 200 M. And if you are in an enterprise, make sure that these logs are backed up or forward to another uh, centralized log server. Supportconfig. Supportconfig is a powerful diagnostic tool provided by SUSE to gather system configuration and diagnostic data. It's especially useful when you need to troubleshoot or share details with SUSE or openSUSE support. Supportconfig is available by default on openSUSE. So if it is not installed for any reason, you can install it. Let's check first if it is there or not. Zipper info support utils. This is the package that supportconfig coming from, and let's check if it is installed already or not. So let's try to, oh yeah, that is to show, and let's see here to install it. And after the installation finish, to generate a diagnostic report, simply run supportconfig, or if you are not root, don't forget to use sudo. So this will generate a compressed tarball in /var/log containing logs and system configurations. This report is incredibly detailed, including information on hardware, networking, services, and more. Once the report is generated, you can unpack it and browse through various logs to find useful details. The output is designed to give you a holistic view of your system's status, and it's very helpful for system administrators managing large or complex environments. It's a real world lifesaver when diagnosing critical issues on a system. Also, be careful with whom you are going to share this file after generated. Okay. So today we have covered 3 essential administration tools for managing your openSUSE system. Chrony for accurate time synchronization, systemd journal D for logging and monitoring, supportconfig for system diagnostics and troubleshooting. These are vital skills for any system administrator, whether you are managing one server or an entire infrastructure. Don't forget to like and subscribe for more in-depth Linux tutorials. See you in the next video. Thanks for watching. Let me know in the comments if you would like to see more tutorials on system administration or any other topic related to openSUSE.